Okay, so we can start. With great pleasure to have here Anastasios Tsiamis. So Tassos is currently a senior scientist in ETH. He got his PhD in 2022 from University of Pennsylvania, and he has gotten his diploma from NDUA in electrical and computer engineering. Tassos was a finalist in 2017 World Congress for the Young Author IFAC Prize, and also in ACC 2019, and he got the Best CDC Student Award in 2022.
Thank you.
Not the first one, thank you.
Thanks a lot for the introduction, and thank you very much for the invitation. So today I'm going to give you some overview of some part of the work that I'm doing, which is in the intersection of learning and control. By the way, if you have any question during the talk, you can stop me if you want to ask. Okay, so just to give you a sense of my background, I guess this introduction already covered it. So I was born in Athens. This is the only Greek slide. So I was born in Athens, and I was in the NDUA, where I got my diploma, and then I moved to the US to do my PhD in University of Pennsylvania. I did my PhD on control and learning. And then I came back to Europe, and I'm now in ETH Zürich, where I was a postdoc and now I'm a senior scientist. Okay. And then, my research interests are, as I said, control theory, learning theory, but I've also done some work in the general areas of stochastic control. I've done some work on risk-aware control, and then also on security, a little bit, touched a little bit some robotics. Okay, so let's give a little bit of motivation. So I hope many of you are familiar with what a controller is. So we have a dynamical system, and then we have some feedback loop that we try to correct or control the system. And then, okay, in the classical control systems, typically we're dealing with some simpler systems, like maybe small-scale systems, or in many cases we might know the model of a system. And typically there are a lot of techniques on how to design this controller. In many cases we rely on modeling. In some other cases, like the PID controller, we rely on some simple tuning rules. And I would say that for many systems this works very well. So if this works, then I don't need to continue my talk, in the sense that for many applications we just apply classical control and we're done. I am here because I'm interested in this question, like how are we going to deal with more complex, let's say, systems? For example, autonomous systems in uncertain environments, or how to deal with complex networks, like the electric network, or again, like how to do something more autonomous, but that involves people as well, like autonomous driving. And in this case, there is a lag, I think.
Have a video or something? Or?
I lost the, I lost the, it doesn't, I changed it here, but it doesn't change there.
Power supply?
Yeah, no. Still stuck. Oh, okay. Sorry about that. Oh, device. For some reason it says device download.
Okay, it's back.
Sorry for that. Okay, I was saying that we are interested in more complex systems. And then the idea is that, okay, based on this traditional pipeline, we're going to use data along with learning algorithms to augment this controller. And the idea is that, okay, we might not necessarily want to use this for simple tasks, but maybe for more complex tasks or tasks where we don't know the system. And again, like in many, we have seen a lot of successful applications of learning-based control in the recent years. For example, you might have seen the success of reinforcement learning when applied for games, but also for manipulation tasks. And then recently we have seen more progress with autonomous driving, and also, like for example in ETH, people have been doing very amazing demos with legged robots by using learning. And I would say that many of those capabilities have been enabled by advances in many fronts, like computation or the availability of huge amount of data and simulators, and of course the development of new algorithms. Okay, and you can see that there is impressive progress in the sense that you can do tasks that you couldn't do before, like controlling this dog-like robot and balancing on a ball. And it's really things we didn't know how to do with simple controllers. But of course, the situation is far from ideal. We can do impressive things, but again, we need to be very careful. We need to apply caution. And okay, this is a toy example, but then if we are dealing with the real world where people are involved, there might be serious consequences. So we need to be very careful how we study these systems and how we argue about these systems. And then again, like when we are dealing with the physical world, many challenges arise. So what is the main obstacle, I would say, when we try to apply learning-based control? So this is the standard, let's say, architecture. So when we want to learn how to control a system, we first perform some experiments, then we collect some data, we perform some learning to learn a control policy. This is at the learning phase. But then, during that phase, we predict, let's say, that the performance of our controller will be good. It's a high performance. But then while we're going to deploy the controller, what we observe is something different. In the end, we get a worse performance. And this is what we call generalization gap. Of course, this term is also in machine learning and statistical learning. But there are many challenges associated specifically with control systems. So we want to see how to deal with this generalization gap. There are many challenges that can affect this gap. First of all, we have sample complexity, which is how many data we need in order to achieve good performance. And then we also have the problem of bias, in the sense that I have, let's say, a controller class over which I optimize. The choice of this class will affect a lot what I'm going to get in the end. Another problem is that things change. So maybe the environment changes as time passes by, or maybe the system changes as time passes by. And so this means that the distribution of the data changes as well. So even if we learn with many data, maybe the data during deployment come from a different distribution. Of course, we also have other very important aspects like the computational complexity. And of course, we have also the problem of robustness. How fragile are these models that we learn? And yeah, the question I'm interested in is analyze all of these challenges and understand better when learning is easy and when is it hard. And then how to make all of these challenges better, right? How to make overall our life easier. And the tools I have been using to do this is tools from control, from learning, and from optimization.
So when you said that, you showed that slide earlier where you have a block for the system. What do you assume that you know about the system? Do you assume you know the equations that govern the system? These are known?
It can be unknown, actually.
It can be unknown.
Yeah, and that's one of the challenges. It can be unknown, it can be complex. So yeah, in particular, exactly in the next section, I will exactly discuss unknown. Okay, so today I will focus on these two blocks. I've been interested and I've done some work on all of those, but I'm mostly on those two. So I will focus on those. Okay, so let's first discuss sample complexity. So I'll give you a high-level overview of what this means. Again, back to this two-stage architecture. So ideally, we would have a lot of data, okay, and then we would get, let's say, the optimal ideal controller, which would, during deployment, give us some optimal J star. However, in reality, we do not afford an infinite number of samples. So we'll have a suboptimal controller with some other cost, Jn. And of course, as we saw in this motivation slide before, this Jn usually is going to be higher. So sample complexity tells you how many data do I need to gather so that I make this suboptimality gap small. So I want this Jn to be as close to J star as possible. And this is for the control problem. We might have a similar version for system identification. So if you forget about learning a controller and all we need to know is a model of the system, for example, the model might be a node, and this is called system identification. Then we have a similar architecture, but instead of learning a controller, we just care about learning the model. In this case, again, the same thing. If I had all the data in the world, I could learn an ideal model, but in reality, I have a finite number of data. So my estimate will be inaccurate. And then again, sample complexity will tell you what is the minimum number of samples to make this model error small. Again, I'm making a lot of assumptions here in the sense that in reality, there is no ideal model, right? Every model is wrong, but forgetting for the moment that there is such an ideal model, then we can define this notion. Okay, so let's study a little bit sample complexity, and I will focus on, of course, I need to make some assumptions to be able to study these questions. Before I go there, let me explain why we study sample complexity. First of all, because we're dealing with physical systems, it's very costly to collect data. So it's very important to know if we have a few samples or not. The other reason why we care about this is we want to compare between algorithms. So we want to know which algorithm is better, if an algorithm is optimal or not. And finally, we can, by studying this sample complexity, we can characterize some fundamental limits that hold for any possible algorithm, which means that in some cases, depending on the system that we have, we might not be able to exceed some fundamental limits, no matter which algorithm we use. And I will emphasize a little bit this part today. Okay.
So your objective is to get the best approximate, the best estimate for a finite data record, or to study what is the desired size of data to get the performance.
Yeah,
or both.
But you can revert.
But what's your focus?
Yeah, for now we'll study what is the number of what is the number of samples that we need in order to achieve this being less than an epsilon, let's say, and this also being less than an epsilon. So we will define some mathematical notions like accuracy.
So can I ask, your objective is the L2 norm between the parameters theta of the system?
Yeah, here it's a bit informal, so I haven't formalized it yet. Yeah, but yes, for example, you could try to learn your system model in L2 norm, but in some other norm as well. But today it will be about L2. I didn't specify it on purpose to keep it a little bit high level.
And there's a unique solution which is minimizes the or could be many.
It really depends. It is important. Today it will be unique because we will have fully observed systems.
All right. Because
it's simpler to discuss today. But all of these problems become much harder when we go, let's say, to partial observed systems where, you have these issues of identifiability and uniqueness and stuff. But for today, it's not a problem. That's not the full generality, but yeah. Okay. So as I said, I will focus on linear systems.
Question.
Yes.
How do you ensure that you don't learn indefinitely, like between theta, cats, and theta, you have a minimum time between the learning and the continuous. That's what they call zero.
Sorry, you said you have a.
How do you avoid zero in the system identification? That is, how do you ensure?
You said Zeno.
Yes, zero.
Zeno behavior. For now, we'll have discrete time systems, so there's no Zeno. To be honest, I haven't thought whether this would be an issue for continuous time.
You can learn
It could be, yeah.
the same thing.
So what typically they do in learning is they use episodes, for example, or they slow down the updates so that you avoid type of behavior. So at least with this real time, this is what you do, kind of thing. So yeah, my short answer is we have to slow down a little bit our updates. Before I go to linear systems, you might be wondering what is new here. This has been studied a lot, right? And many, I guess, you in the audience might have come across a lot of these algorithms that I will talk about, and maybe you came across system identification or adaptive control. So this has been studied before, but it has mostly been studied in the asymptotic regime. So when we have as the number of samples goes to infinity, and there are many results on which we rely a lot. Now, what is new here is that we have a finite sample point of view. So we assume that this number of samples is finite. So we're going to have results that hold for any n. And yeah, by going with finite samples, you can have a better picture of the transient, and you have results that hold for every n. But also, for me, the most important perhaps is that you need language that is more close to what learning people use today. So yeah, statistical learning theory was finite from its birth. And then this is the language that people use nowadays. So it's good to be able to have a bridge between control and learning and speak their language. And yeah, so this led to a magazine article that we wrote, trying to unite those two fields and to have a point of reference, that bridges this language. But I will not talk about this today. Today I'm going to talk about mostly the fundamental limits. Okay, so as I said, we will simplify a little bit the setting to be able to argue about sample complexity. So we study linear systems. So X is the state, U is the control input, and W is some disturbance. But we assume it's IID, stochastic, and in particular Gaussian. And then, as we discussed, we will assume that this is an unknown system. Okay. So, going back to the previous architecture, what we do is we perform some experiments on this linear system, we get some data. We can study two benchmarks. The first one, as I said, is system identification, where we try to estimate the unknown matrices. Here, let's say you estimate only A and B. Let's forget about H, but you could also have H being estimated. And the other benchmark is, let's say we try to learn a controller. And you might be saying, okay, linear system is a very easy class of systems. Why not go nonlinear? Yeah, it's too simple. Yes, it is simple to analyze, but it's very valuable because it's also rich enough so that we get some insights of what can go wrong or what can be the challenge and so on and so forth. Okay. Any questions so far?
So your variable x is in general a vector?
Yes, it is a vector.
Okay, and they're all lumped in one point in space. It's only the time.
Yes.
Time.
It's time domain, yeah. Okay, let's focus for now on system identification. And then I didn't talk anything. I didn't say anything about the experiments. What are the experiments? So we have to actually specify that as well. So in order to learn, we need to collect the data, and this is really, really important. So to do that, we need an exploration policy, let's say, the data gathering policy. We will only pose a limit on the total budget that we have. So the total energy of the input can be upper bounded by some budget. Because if we could afford infinite input, then that's kind of then maybe we could identify theoretically as well. So kind of increasing the budget is kind of equivalent to increasing the number of samples. Okay. So that's the pipeline. A simple implementation to realize this pipeline is we could use just white noise for the exploration policy. For example, it can be IID Gaussian. And we could use, for the learning algorithm, we could use the very well-studied algorithm of least squares. we'll try to minimize the square error. Okay. And then just to simplify the discussion, I will use theta to denote A and B. Okay. Now, let's go, and then we'll use this. So, what is the first result that we can present? So, if we replace the exploration policy with a simple white noise policy, and if we replace system identification with the least squares, then we can get a statistical rate for this simple implementation. So we get something like that. With high probability, we get a small error for the recovery of the parameters if we get a number of samples that is larger than this quantity. And I will try to unpack every term. First of all, sigma W is the noise level, so how big this W noise is. Sigma U is the exploration budget. So what this says is that the more noise I have, the more samples I need. The more budget I have, the fewer samples I need. It also depends on the state dimension. So as we discussed, the state is a vector. So dx is like the size of this vector. So what this says is that the more complex the system is, the larger it is, the larger the number of samples. And epsilon is the accuracy with which I need to recover my parameter. And this 1 over epsilon squared is a very standard error in statistical learning when you do regression. Now, there is also this C system. It's like a system-specific constant that depends on the unknown system. I will explain a little bit later what this is. But for now, let's not pay too much attention. So, seeing this, so this actually was, this result is due to some people that were working in computer science and statistics. So these people didn't necessarily have a control theoretic background. And they said, okay, seeing this bound, they said, okay, my number of samples is linear with the dimension, right? So it seems that, the scaling of n is O of dx. So here, O is a big O notation. So ignoring every other parameter, it seems linear with the dimension. Sorry for the font is a little bit small, but yeah, that's what I'm saying. It is a linear with the size. So these people said, for example, after observing this, that okay, system identification is an easy problem. It scales linearly with the dimension. So let's see if that's the case.
Sorry, if you have a complex system, right, you may not even know what the dimension is, correct? I mean,
So you know, because it's fully observed, you observe the state.
so
you know the dimension.
You know all the variables that are involved in the system.
You know the dimension, but you don't know the A matrix, the matrix A and matrix B.
Yeah, but in physical systems, you may not even know the
Yes.
dimension.
If it's partially observed, yes, you don't know. And then you have even more challenges. But let's for now, but it's interesting that even for this system, which you know the dimension, you might have weird things happen. Okay, I'm spoiling a little bit. So let's simulate the least squares algorithm for this system and the simple implementation. And let's measure the number of samples needed to reach a good precision. So the theory, or at least what prior work argues, is that we need a linear number of samples. So after performing some simulations, what we observe is something different. Actually, for this system, we get an exponential number of samples. So this is a log scale. So we see that as we change the dimension, as we move towards higher dimension, then the sample requirements increase exponentially. So it seems that we have a curse of dimensionality.
What do you plot here exactly?
So this is the number of samples needed to reach, let's say, the precision 0.1.
Okay.
So this is the blue line, let's say.
Okay.
So as I increase the state dimension, let's say here I need 150 samples, but here I need 1,000. But this increases very, very rapidly. And it doesn't agree with what prior work argues. Okay, so is the theory wrong? No. It's like we missed something from the previous analysis. And just going back to the requirements, what did we miss? We didn't say what this system theoretic constant is. So what is this constant hiding? So what is this constant? So this depends on a quantity called controllability Gramian. In case you know what this is, But if you don't know, just think that this is like the sensitivity to control or to excitation. Like how when I poke my system, how easy is it to change, kind of. And if this is also too complicated, maybe this is more familiar. The signal to noise ratio. So gamma captures how you modulate the input as it passes through the dynamics. So overall, you can think about this ratio as the signal to noise ratio. So the effective signal that excites the system versus the noise. You can view this requirement as SNR inverse times the dimension divided by the x.
Gamma is a function of the model.
Of the model.
Not of the estimate.
Yes, of the true model, of the unknown.
Okay.
Of the
So
true
it's
unknown.
constant.
Yes.
So the constant is constant.
It is constant, but it depends on the dynamics. Yeah.
It has correlations.
Yeah, it
What
hides
correlation?
exactly.
Fine.
Yeah.
But for a specific model,
Yes,
constant is
yeah,
constant, right?
Yeah.
So why do we get the exponential curve?
Because I changed the dimension, so I changed dx. So just to go back here in the bound. So you have this constant, okay, and you have this dimension. So as you increase the dimension, yes, you change this, but then also you have to change that.
Oh, you changed
The parametric, let's say.
Okay.
But
I see.
how? There are many ways you can change that. right?
Yeah.
Because you change the matrix essentially.
Yeah,
Actually,
exactly.
we changed the matrix, so
Yeah,
it's not a
yes.
constant.
Yeah. No, but
Over D, it's not a constant over D. To be
Yeah. No, but okay, what I meant is like, if you fix your theta, then it depends on theta. Constant in the sense that if you keep it the same, you round the algorithm for a different number of samples, it doesn't change its constant.
So D is hidden somehow in theta.
Yes, exactly.
In the constant. So this reappears in the theta.
Yeah, exactly.
Okay.
Yeah, but don't you also have to change the epsilon under this scenario?
So you keep
To be fair?
we did it for many epsilons.
Right.
So,
Then as theta.
yeah, so, okay, I'm not showing all of the details, but we have an unknown here. So let's say this is unknown,
Yeah.
the upper left element. And you keep epsilon the same because you want to learn it with the same accuracy as you increase d.
Yeah, but the norm
It's one
in
parameter.
10 dimensions, norm bounded by epsilon in 10 dimensions, and the norm
Yeah.
in 1,000 dimensions
Exactly.
bounded by epsilon very.
Totally. So that's why what we compare is the error here for one element, only the first entry. Yeah, it's a bit high level. I'm not showing all the details, but you're absolutely right because the norm scales with the square root of the dimension.
So this epsilon has to do with only one element, not the entire matrix.
Yeah, for this example.
Okay.
Yeah.
But I still don't get, so when you change this matrix A, right, is there some particular structure that you maintain as you increase it?
Yeah. So here you have this special structure. So this has a very particular structure. It has everything is zero apart from the diagonal and the upper diagonal.
So if one changes that structure, then
No,
perhaps.
this for this specific structure.
Okay, so, but what I'm asking is, then perhaps that plot would also change.
Yes, of course. Yeah. So this relies on the structure, and I will explain exactly now that part. Yeah, very good observation.
So is this reconfirming the well-known observation machine learning, the curse of dimensionality? Because that's what the flow says.
Yeah. So in linear regression for machine learning without dynamics, it is well known to be easy because people have established there that is linear with dimension. So people developed some results for this and said, okay, it's also easy here. But what I want to emphasize is that the dynamics actually might play a dramatic role in changing this. Yes, it's true that machine learning, you can have curves of dimensionality as well, of course, but not for linear regression necessarily. Because there the complexity of linear matrices is bounded by these dimensions, kind of. Okay. So what I'm arguing here is that the dynamics matter, and I think that we shouldn't ignore them. And prior work implicitly assumes that this signal to noise ratio is right. And then, okay, that's exactly the question, to go back to this example. Why is it hard? It has a very special structure. First of all, it is very underactuated. So we only actuate the last state here. And then, as you can see, let me go through the cartoon. So let's say we apply an input of 1, okay? And we have a dimension of 4. So what will happen is that the first state will be 0, 0, 0, 1. And then as we move to the next state, it will be 0, 0, 0.5, whatever the last coordinate is, and so on and so forth. As we move upwards, as the information moves upwards, so as we go from the bottom to the top, the information gets exponentially attenuated. So we have exponential damping as we move up and up, which means that then the signal on the top is exponentially small, or if you want, the SNR will be very poor for this system as we move towards the elements which are closer to the top. So, going back to this, what I want to argue is that in prior work it was assumed that SNR is good enough so that it's sufficient to select this number of samples. But we show that there are systems where this doesn't actually make sense. There are systems where this SNR, like this example, is very, very small. So in this case, the theory says that it is sufficient to select an exponential number of samples. But, yeah, so you see a dramatic increase in sufficient requirements, but this is just a sufficient condition. It doesn't necessarily say that it's necessary. So the question is this condition necessary? And is it a problem of the algorithm? Because we used a very simple, naive implementation. And then our result states that actually it is a fundamental limit. So no matter which algorithm we use, no matter which excitation, which exploration policy we use, the only way we can reach this accuracy is that we have to meet these sample requirements. So this exponential hardness is a fundamental problem. It wouldn't change even if we use a different algorithm or a different exploration policy.
So for algorithm here, you mean the least squares?
Yeah. No matter.
In this case, isn't least squares equivalent to maximum likelihood?
Yeah, in this case it's optimal, so it's easy to. I mean, you could also go with other tools like asymptotics and the maximum likelihood. But here we use finite sample tools, but it is possible to show this actually also using maximum likelihood. Yeah. So what is the moral of the story here is that it is possible that we don't have a linear complexity, and we have exponential complexity. And this can be observed for underactuated systems. Again, not all of them will be very hard, but some of them. And the main reason why this holds is that it's very hard to excite the system, so they have a very poor SNR. And then the proof is based on something called minimax lower bounds and some information theoretic tools. I will not go into details because I spent a lot of time. Okay. Any questions so far for this? Okay. So this is for system identification. So one can say, okay, sure, it's very hard to estimate, let's say, for this system, this model, but how is this important for control? What if we do control? Just for the interest of time, to present also some subsequent work, I will go very fast through that. So let's say that our problem is to minimize this control cost, which is like the linear quadratic regulator. In this case, if we knew the system, then we know how to compute this gain, this linear gain. It's just a function of the unknown parameters. But this requires, of course, the unknown parameters, which we don't have. So we will have to learn how to do that using data. Okay. Just to go very fast, the same conclusion actually holds also for this problem. And then, yeah, what we're interested in is the suboptimality gap. So the same conclusion holds, and let me go a bit fast, just to spend more time in the subsequent stuff. Okay. So let's study again an underactuated system. This time, instead of having damping, we will have high gain. So this time, notice that this upper diagonal has very high gains. So if we repeat the same experiment as before, start from 0, 0, 0, 1, then we have 0, 0, 2, and then 4, and then 8, and so on and so forth. So this is a very sensitive chain. So as we move up the chain, we have exponential amplification. And this makes our system-theoretic constants, again, very large. We have a similar bound as before. So what is the main result that we have? For any possible algorithm, if we want to have a very small suboptimality gap, then it is unavoidable, again, that we have a number of samples that it increases exponentially with the system dimension. And this is again a fundamental limit for any algorithm in any acceleration policy. And in this case, again, underactuated systems can be the bottleneck. And then we have the opposite problem. This time we have big sensitivity to excitation.
Is it still sufficient?
This is necessary.
The proof is for the necessary. Okay.
Yeah, it's not sufficient. Yes, sir.
Hmm?
Yeah, I skipped the sufficient for the industrial science.
In both cases, the matrices that we used are ill-conditioned.
Yes.
So the results that we present look very much related to the condition of
100%.
Okay, I'm wondering, as Mr. Anastasios, instead of 2, you had another number in your matrix, maybe 4. The 4 there is sufficient.
Yeah, this relies on the specific construction. So this 4 is because this system. So I didn't have time to go through the details, but we call this algorithm. So the way you prove these results is you restrict your algorithm to be non-trivial. So it has to work for a neighborhood of systems, let's say around your example. So for any algorithm that doesn't work only for a specific system, but works for a neighborhood around the system over which we construct a difficult example.
So we don't cover the case where instead of 2, you should 3 there.
Yeah. So if we, so there are 2 ways to go with this. Either you have to do local results around the specific example. So in this case, I rely on this structure, and this is why 4 appears. This is one way to go. The other way to go is to have global lower bounds, in which you get big classes. So let's say we get all the underactuated systems. So in this case, it's still a valid bound, right? Because this is included. It might not be tight because you might have much worse.
Is it possible to derive a bound directly related to the condition number, irrespective of the form of the map?
That will be something interesting to see. I've seen that it depends on the condition number, but when constructing examples like this, it's hard to make it appear in a nice way. But it will depend on the condition number of the plant implicitly. But again, the honest answer is that this depends on the specific construction with the tools. And you can repeat this procedure with different examples. But here also you could say that if I give you the class of all underactuated systems, then you will have exponential complexity in the worst case. That's this.
Out of curiosity, what is the Van Driessen one?
Sorry,
The Van Driessen one.
It's like camera, but you have a prior. So camera lower bound is without any prior.
And the epsilon is not that true square.
Yeah, here we have the cost. That's why. If we had before we had the parameter estimation. Here we have the cost. That's why before it was with the square, not with that. We had 2 difficult examples. We have more examples in other works, but typically the counter examples we construct are chains of underactuated systems where you either have low gain or high gain. So you have either too little or too much sensitivity, which is related to the condition number of the, let's say, controllability gradient. Yeah, the takeaway message is that too much sensitivity or little sensitivity can both hurt us. And yeah, the insight from this line of work is that, in general, the easiness or hardness of control impacts the easiness or hardness of learning. So, when control is hard, then this controllability gradient is ill-conditioned, for example. And this implies also that it might be hard to learn. Another message is that these system-theoretic constants matter, and they can be the bottleneck of difficulty. So it changes a little bit the problem compared to traditional machine learning, where you don't have correlated data. And yeah, for me, another message is that these fundamental limits show us that just by using algorithmic solutions, it might not be enough. In some cases, if the system is poorly designed, sure, I can improve a little bit my position, but there are some limits I cannot improve unless I change my design. Which brings me to the next point. So if something is not working, then we have to make sure we design our system properly. So one of the goals I would like to see in future work is how we could use these bounds to inform system design or redesign. For example, we might want to place some sensor or some actuators, or we might to design the network in a more complex system. Maybe we need to take all of this into account in order to do that. So this is something I'm currently studying. And of course, we didn't address partially observed systems. For example, we know the system I mentioned in this semester. So we're currently also studying partially observed systems where things are much more nuanced. Of course, this was for linear systems. In future work, I want to see how we can extend this to nonlinear systems. And then another important part that is the effect of bias. So we assume, for example, that there is, for example, that our known model exists, that an ideal model exists. Maybe no ideal model exists in the sense that we have some bias. Okay.
And in this last bullet, you also include the assumption of the structure that you assume for the model?
So the assumption of the structure was just to prove that there exist hard systems. This was for the necessary conditions. For the sufficient, we didn't assume any structure. So you don't need to have any structure to derive some sufficient conditions.
So can I ask, so I guess, like, do you have any insights if you take your linear equation and just pass it through a rectified linear unitary U, as we call it in machine learning, like activation function, which is 0 for negative inputs and positive for positive inputs, but would make essentially your net non-linear. On the other hand, it's like a small change. Any insights?
Yeah, some people have studied that actually. Well, not me. But this, I think they call it generalized linear models or something like that. But they have studied, one non-linearity with a linear inside. Is this?
Yeah, basically you have one hidden layer here.
Yeah. So you can argue about the systems.
There must be some connection with recurrent neural network because the equation that you have is basically the equation that updates the state, the hidden state of recurrent neural network, missing an activation function. So I'm wondering if there's any connection with the RNNs.
That would be something definitely to explore. Again, as I said, some people have already studied the one-layer version. So perhaps, some of the tools are not directly applicable, unfortunately. So I'm not sure right now I would solve it, but for one layer at least I know that people have studied. But it makes sense to formulate it as a problem. So we studied this architecture where, as we get more data, we hope things can get better. But this relies on two assumptions. First, that we have some statistical model of the uncertainty. And then second, we assume that the system remains the same. But in reality, what we might face is something like this. So although we plan for a system 1, let's say, what ends up happening is that we have a different system. So the system changes. So in this case, what can we do? So we can continue learning. So we can get more data online. and then we can do more learning online. So we will have deployment and learning simultaneously, and this is the so-called online architecture. And then I'm interested in using techniques from online learning to study this problem. And then these techniques from online learning also give you a way to deal with more unstructured uncertainty in the sense that it's not necessarily stochastic, or it's not like a minimax disturbance. So let me take, I don't know how much time, okay, maybe I need to go very quickly so that I look with some outlook. So yeah, we studied tracking control, where we have an unknown moving object. So in many of these applications, you might be dealing with objects that move but are unknown and non-stationary. And then they do not necessarily follow a statistical model. So although there is some uncertainty in how people move, they do not necessarily correspond to a statistical noise. So to give you an idea of the setup, and then I will just show you very quickly. So what is online? What is the formulation here? So we want to track this unknown object, but we don't know a priori how it will move. So what do? At any time, at any point in time, we just know the current position. Okay? And we have to make a decision. So let's say we decide to move right. So let's say we take an action. Now, only after we take an action, we observe what the target did. Okay? So we suffer from some error, which is like the tracking loss. And we repeat this over and over again. So at any point in time, we first make a decision, and then we observe what happened. And then we want to minimize as much as possible this tracking error. So what is the challenge with that? So if we use classical optimal control, we can compute the optimal input, but it depends on the unknown target. It depends on the future target states. However, we know the functional form of this input. So we know these linear gains, and we know the feedback form. So the bottom line is that because these are unknown ahead of time, we cannot realize this optimal input. So we will have to somehow change what we do, because we have to have causal. So and then we suffer from the so-called regret, which is like what my cost is versus what I could have done if I had the optimal one. Let me skip. I just want to mention that with these approaches, what we can do is we can have theoretical guarantees. So we can get some so-called regret bounds. So we can upper bound this regret that I mentioned with some theoretical bounds that depend on the complexity of the dynamics. So here we have like a term that depends on the target dynamics. So let's say the target can be modeled as a linear system. Then we can get theoretical guarantees that will connect this regret to this complexity of the system. Okay, what is different compared to other works, so previous work, is that this guarantee is called under non-stationary environments. And yeah, the novelty with respect to the classical literature of like learning this model, let's say, is that we have non-stationary. Yeah, sorry for that, I was going very fast.
Non-stationarity here, you mean in the noise term?
Yeah, so here this target changes, so dynamics changes. And we don't necessarily have stochastic. So this guarantee is called for any arbitrary target that has this dynamics. We also perform some simulations. So the bottom line of these guarantees is that if your target is very easy, so if it has very simple dynamics, then we can track very well. So if these dynamics are constant, for example, we can track very well. Now, as we increase the non-stationarity So for low non-stationarity, we can still track well, but when things change a little bit, we are off, and so on and so forth. Or if it's very highly non-stationary, then we are still kind of close, but you know, we can miss the target in some sharp terms. And we also implemented this figure 8 using drones. So in this case, the target was virtual, in the sense that we simulated this whole game of not knowing in advance the target. So we also implemented these algorithms on a real drone, and it can be implemented in real time. Okay. Again, we limited ourselves to linear dynamics, so that's one limitation. We assume that the target is non-reactive, so it is not. It is like unstructured, but yeah, we didn't necessarily take into account that it can react to our actions. So if we treat it as reactive, we might get something less conservative. Yeah, so in future work, I would like to see something with nonlinear dynamics, and also another important thing we are currently studying is control with constraints. And we didn't have noise in the dynamics of the system, we only had noise in the dynamics of the target. So another thing I'm studying now is, well, we have also noise in the dynamics of the system. Okay, so we also applied some of these techniques for pedestrian tracking. In particular, we used some pre-trained offline models from Berkeley, and then using online techniques, we combined the predictions of the generative models online using these techniques. So our goal here would be to then, let's say, if you predict a pedestrian, then use it for the drone to track, let's say, the pedestrian. But I think, in general, using these techniques of online learning could be useful for human-in-the-loop systems. And in general, I have some ideas how to combine generative models, let's say, for control, along with these techniques to be able to fine-tune. Okay. So let me give you some outlook. Again, I'm interested in all of these challenges, and yeah, my background is using these techniques to solve them. And again, one of my goals is to to lay some foundations to use the theory to understand and improve the landscape. And I'm interested in applications like robotics and human intelligence. So my goal would be, if I start as a faculty, to apply initially for a funding, for example, for a university starting grant, or look for opportunities in Greece like ETH. So I would spend my first, let's say, year, 2 years trying to establish grants. Then I would like to also exploit my network in many places in Europe, also in the US. But recently, yeah, I've known a lot of people around Europe, so for potential collaborations. And also my network in Greece, I have points of contact in some recent initiatives in Archimedes, and which is like for an AI center, and Aeron, which is like a recent center for robotics. And yeah, exploit the network for funding opportunities and collaboration. And then with regarding teaching, so I had a lot of experience in ETH, where I'm teaching, since I started, I'm teaching the course Linear System Theory. So I've taught so far for this course for 3 years, along with John Ligeros. And this is like a more mathematical course where we try to establish control system theory, but from a more mathematical perspective. We also cover analysis, linear algebra, and differential equations. Then I was also a TA before at UPenn for optimization courses and linear system theory again. So yeah, my background is control theory, optimization, signal systems. I can also teach machine learning stuff, anything involving applied math. And yeah, as you saw a little bit from my presentation, I have more experience with theory. So just to give you some idea of potential courses, sorry, this is in Greek again. So yeah, any math course like calculus or linear algebra, probability, signal systems as well, control systems are easy to teach with little preparation. I could also teach multivariate analysis with a little bit of more preparation. And of course, I'm open to other stuff as well, given more time. Yeah, if there's a need for another course that is not in the list, also happy to discuss. And then, yeah, if there are some ideas for improving or adding more stuff for the lab of control, that's also I'm happy to discuss. And then similarly for the elective list, yeah, differential equations, linear systems, optimization, all of these are very close to my background. And I'm also interested in robotics or some other math courses, dynamic programming, reinforcement learning, but also anything involving random algorithms or statistical models is good. And yeah, just to save a bit of time, yeah, similar for the graduate course list. And then if I would introduce, I have some ideas, I could introduce new courses like learning and control or online convex optimization. And then there is a new course in ETH happening, which is a very good idea. So they try to compare all the different control techniques beyond PID and LQR. So if I want to solve a complex control task, which technique is the most appropriate? And they try to also incorporate some ChatGPT prompts. So they try to exploit this new technology to, instead of avoiding it in the course, they try to incorporate it in teaching. So I would be interested in seeing how to implement that too. Okay, I will conclude now. Sorry for taking more time. Thanks a lot for your attention. These are some of the papers on which I based my talk. Happy to answer any further questions.
Any questions for Tassos? Yeah.
So Tasso, thanks for the presentation. It was quite nice. What I wanted to ask is if you have kind of a different system where you don't actually know much about the system, basically you don't know anything about the structure of the matrices, and you want to infer those matrices aiming to detect connectivity between different elements. So this is something, for example, that would be useful in causality inference. Do you have any ideas about?
So I mean, you could use this least squares. I mean, yeah, of course the least squares algorithm is around for. It's not our development. Yeah, you could still use these results to argue about these systems, and then without any structural information, all that you know is that the dimension, the size, will of course matter. Now again. So your question is if you can further connect. Yeah. So depending on the structure of the network, some networks actually like these ones that I saw, which are like underactuated. Maybe for some systems like this, it might be hard to infer some of the connections, like especially if they're further away from the inputs. So if there are far away nodes, this kind of results show that it is possible that it's hard to infer, let's say, the far away nodes. But other than that, yeah, you can still, in principle, recover the structure from that. Yeah, like the standard, the sufficient conditions say that you can recover this matrix with some accuracy. So yeah, if this accuracy is small enough, then I guess you can recover. Now, if you know that the matrix is sparse, there are some other results that use some L1 techniques. There exist some results that can tell you, for example, that okay, if my matrix is sparse, then automatically I will have smaller complexity. But then you need to know that you have some sparsity.
And how about if you have systems that have coupled oscillators, for example? How would you go about with that kind of system?
You mean like to do what with a coupled?
Again, to try to infer potential connectivity between the different oscillators.
Yeah, so again, because this setting is identifiable, so it's very important now. We have fully observed systems, and everything is in the model that we have, the noise model. And as I said, one of the limitations was the realizability assumption. So what I mean by this realizability assumption is that with this assumption that we introduced here is that you can really identify everything properly. So there is a unique theta star that gives you this prediction. So yes, in theory you would estimate that. If you can formulate as a linear system and so on and so forth. But because you have identifiability, you would be able to recover exactly in the limit. The problem, I think, arises when you go partially observed. Then, yeah, when you might not have identifiability. So you might have multiple different systems giving you the same prediction. So in this case, it's probably impossible without further assumptions.
So for the oscillatory systems, you would still put them in that kind of first order linear.
Yeah, for example, I'm not sure if I'm not familiar whether you can do that, but if you could do that, yes, you could apply these results. Yes.
Any other question?
Okay.
No other question?
We are
Okay,
sorry.
so thank you.